Hello again, and welcome to part two of our solar system, the video series that will run three parts. Last time, in part one of the series, we took a look at several different things. Space basics, I called them. We talked about the universe and how it is the vessel in which everything that we know is contained. And there are two parts to the universe: the observable, that which we know, which we see, and then there is the larger part of the universe, the unobservable, that which we know is out there, but we really have no idea what is in it or what it's contained inside of it. After the universal level, in other words, we have galaxies that are within the universe. And of course, our galaxy is called the Milky Way. The galaxy that is closest to us right now, Andromeda, is another galaxy. And there are many, many more out there that we just don't have time to mention here. Now, within galaxies, we have solar systems, and I told you that I would refer to those as planetary systems or cosmic neighborhoods. And within our solar systems, that's where we find our planets, our moons, our stars, comets, and all of those other sort of natural satellites that we find in space. After we broke down the composition of the universe, we talked a little bit about the sun. We watched about a 5-minute National Geographic video that talked a little bit about the fusion process by which the sun creates its energy. It talked about the size of the sun with relation to the planets and the other things in the solar system. And that's sort of where we're going to pick up today. We're going to take a look in part two here with we're going to compare planets and stars. We're also going to compare the planets in our solar system with each other and with the size of the sun. And the last thing that we're going to do in part two is we're going to take a look at the vast distances that we see when we gaze out into space. With that, let's get started. When we talk about planets and stars, Dave Rothstein of Cornell University has suggested two main differences between planets and stars. Okay, so first of all, let's take it back to the extreme basics here. Earth is the planet that we live on, correct? And our star, which makes up the sort of anchor for our solar system, is the sun. Okay, so what's the difference between, say, the Earth and the sun? Well, Rothstein says stars like the sun, first of all, undergo nuclear reactions, which means that they produce their own heat and their own light. All right, now to have enough heat to burn, stars have to be at least 75 times the mass of the planet Jupiter, which in our solar system is the top dog. It's the largest planet. So that's one way that stars are different than planets. Okay, they undergo nuclear reactions. The second way that a star is different than a planet is a star forms when a cloud of gas around what we call a nebula collapses due to the force of gravity. So the next question you may have, Mr. Martello, well, what's a nebula? Well, a nebula is basically a giant cloud of dust and gas in space. Some of these nebulas form from supernovas. They're a result of a dead star. Others are just regions where new stars are forming. So what you see here is a beautiful image taken by the Hubble Space Telescope called the Eagle Nebula. And if you look here, you see these three distinct pillars. Those are referred to as the pillars of creation. So you're looking at the place where a star will be born, okay? Now, so stars, remember, They undergo nuclear reactions and they form from nebulas. Now let's contrast that with planets. Rothstein says planets, first of all, they don't undergo nuclear reactions. They do not produce their own light. They may produce a bit of their own heat. The Earth actually does produce a bit of its own heat, comes from the core of the Earth, but that would not be enough to sustain it without the light and the heat from the sun. Now, planets form when the leftover material in the disk around a pre-existing or an already forming star begins to condense around a rocky or an icy core. So planets themselves don't form from nebulas. All right, planets form basically from all the leftover material that a star does not scoop up in the region. And those are the two biggest differences between planets and stars. It's the fact that stars burn, planets don't, and they form in completely different sort of conditions. Planets also have different sizes. We can see, when you look up into the night sky, we often say, wow, look at all those beautiful stars shimmering up there. But what you don't realize is that not everything that you see is a star. As you look up into the night sky, you are also seeing planets. And those planets are reflecting light. Some of them are planets in our solar system. At this time of the year, and we're in late August right now, currently at night, if you look into the southeastern sky from here, you can clearly see Jupiter and Saturn practically right next to each other. All right, so not everything that you see twinkling, shining, sparkling in the night sky is a star. Okay, you could also be seeing, some of them are stars, obviously, but you'd also be seeing other planets, moons, things like that. Even the International Space Station, some man-made things. All right. So planets can be seen in the night sky not because they generate their own light, but because they're reflecting the light of a nearby star. All right. Moons, comets, and asteroids will reflect this light also. And objects in the solar system have very different sizes. An asteroid that is in a particular region of the solar system, in a particular cosmic neighborhood, might be the size of a mountain, which might be about 1/1000th of Earth's diameter. Some planets, on the other hand, out there are 10 times the diameter of the Earth, maybe even larger. As a matter of fact, the largest planet in the observable universe that we have pinpointed as of right now has a very boring name. It's called HD 100546b, and it's a gas giant, and it's 7 times larger than Jupiter. That's huge. All right. Remember, Jupiter is the largest planet in our solar system. Okay. But there are planets out there even bigger. Now, the sun is huge compared to even the largest planet in our solar system. The sun's diameter is 100 times bigger than the Earth's. That means you could line up around the equator of the sun, you could fit from one edge to the other 100 Earths. Okay. And the sun, our sun, is actually an average sized star. It's actually classified as a yellow dwarf star. And, stars range in size all the way up to red giants, and even bigger than that, yellow hypergiants. There are just massive stars out there. For a long time, we believed that UY Scuti was the largest star in the observable universe, but more recent data has pointed towards a different star that's about 20,000 light years away from us, called Stephenson 2-18. And it is some 2,150 times larger than our sun. If you would drop Stephenson 2-18 into our solar system right now, its surface would extend all the way out to Saturn. That's how big that star is. Okay, so there are things much larger than what we have in our cosmic neighborhood out there. So if you take a look at this here, you'll see, and this is not meant to show distance. All right, so the distances on this this image here are not to scale. However, the size comparison is. All right, so if you look at the first 4 planets, you see here, if we look at Mercury, Venus, Earth, and Mars, you see quite small, all very small, especially compared to the size of the sun over here. All right, but then we get to the 4 outer planets here, Jupiter, Saturn, Uranus, and Neptune, and you see that they're much larger. Okay, I want to come back to this image later on, and I want to have you thinking about the composition of our solar system here. If you take a look at the planets, do you think it's an accident that the 4 inner planets are much smaller than the 4 outer planets? Don't just look at this image and say, whoa, Jupiter's big, Saturn's almost as big, but the sun's bigger. I want you to think about maybe why. Is there a reason that those 4 planets closer to the sun are smaller and those 4 planets farther away are larger? We'll come back to that idea here soon. But the one thing that is not much up for discussion is the fact that the sun is the big boy on the block here. And, Jupiter is the largest planet, but it still is dwarfed by the size of our sun. All right, so planets have different sizes. They also have much different distances. All right, not all planets are the same distance from each other, like you see in a lot of images and a lot of graphs. The distances between most objects in space are huge in comparison with those objects' size or their diameters. In other words, the distance between 2 given planets is going to always be much larger than the size of either one of those planets. What do I mean by that? Well, distances in space are so large that scientists had to come up with their own unit to measure them. And I personally think that this is a good one because a lot of times when we're studying units, they don't really make much sense, right? But here, what scientists did was they took the distance from the Earth to the sun, which is 93 million miles, and they say, hey, that's 1 AU. Now, AU right here stands for the astronomical unit, okay? So 1 AU is equal to 93 million miles, or the distance from our sun to our Earth, all right? So if we take this idea of the AU, Mercury is less than a half an AU from the sun, all right? So if 1 AU is 93 million miles, then half of that would be what? About 46 million miles from the sun. That's how far the closest planet to our sun in our solar system, Mercury, is still 46 million miles away from the thing. Jupiter, on the other hand, is 5 AU from the sun, all right? And that's 5 times 93 million. So that's just an outrageously big distance from the sun to Jupiter. How about Neptune? Neptune is 30 AU from the sun, all right? That's 30 times 93 million. And that'll give you the distance of Neptune from the sun. Planet 9, Planet X, whatever you want to call it, the planet that we figure may eventually replace Pluto as the 9th planet in the solar system, is 200 AUs from the sun during its closest orbit. and it could be as far as 1200 AU at its most distant orbit. That is way out there. All right. So if you look here, you can see this is a little bit better indicator of the distances of the planets from the sun. If you look here in the middle of this image, that would be right. Let me get this on here, this highlighting thingy again. There we go. Right here in the middle, Earth, Mercury, Venus, the Sun, Mars, Jupiter are all contained in these yellow orbital areas here. Then you see Saturn way out here in the orange, Uranus even further, Neptune way out there. All right, and our friend Pluto, you can see its odd orbit taking it way out to the edges. Well, not really the edges of the solar system. It extends much further than that, but Pluto is out there, okay? And if we throw Planet 9 into the mix, now, if you take a look here, the sun and all of the known planets are all in this bright yellow area, all right? And Planet X, or Planet 9, is way out here. And you can see in this image that we got from Caltech that it, excuse me, we know that one Earth year refers to the time that it takes the sun to make the Earth to make one complete revolution around the sun. Okay, so it takes Planet 9 or Planet X 20,000 years to orbit the sun once. All right. Now, that would mean that on Planet 9, each season would be approximately, 5,000 years. All right. So 5,000 years per season. Interesting. Evidence is still coming in for Planet 9. Right now, it's so far out there, we haven't seen it. But based upon a lot of mathematical calculations and based upon the behavior of other objects out in that area, we're pretty sure that Planet 9 is out there. Okay, so vast distances we see out here in space as we observe our solar system. Now, we know the 8 planets in our solar system, and there's been a lot of talk recently about it traveling to Mars, about a manned mission to Mars. And I think that we kind of get lost in all of the tech talk here, and we don't quite understand really how much time it would take to get there. All right, so let's take a look quickly here at light speed and space travel. All right, so light travels at a speed of 186,000 miles per second. That's equal to 670,616,629 miles per hour. That's pretty fast, all right? As a matter of fact, we believe that there's only one other thing in the universe that can travel at that speed, and that's gravity. All right. Nothing else can travel the speed of light. All right. Except for light itself and gravity. So let's take this into account. If you were traveling at light speed, you could circle the Earth at the equator 7.5 times in 1 second. All right. Let's compare that with how fast a commercial jet or an airliner travels. If you were traveling that same distance in, let's say, an American Airlines flight, it may travel at about 500 miles per hour, and you could get across the United States in about 4 hours. So you see, traveling at light speed, you could circle the equator 7.5 times in 1 second, whereas traveling in an airplane at some of the fastest speeds, you can just cross the US in about 4 hours. So our technology is really nowhere close to getting to these speeds. As a matter of fact, if you think about how fast light travels, When we see an image of the sun, we're never looking at the sun in real time. It actually takes light 8 minutes and 20 seconds to travel from the sun to the earth. What's that mean? In theory, the sun, if it burned out completely, we here on earth would not know. We would not get the last beam of light until 8 minutes, 20 seconds after that. All right. So I'm just trying to give you an idea here of how large these distances are in space. All right. I mean, light travels fast, 186,000 miles per second, and it still takes 8.5 minutes to get from the sun to the earth. So when we talk about light speed and space travel, what exactly are we talking about here? Well, how long would a trip to Mars take? Let's consider these facts. Mars, at its closest point to Earth, is 33.9 million miles away. Currently, that's a 180-day or a 6-month trip, one way. So if you want to go to Mars and back, that's a full year on your space shuttle, just in the time it takes to get there and back. Currently, our fastest spacecraft was NASA's New Horizons probe. It traveled at about 36,000 miles per hour. And if you could have ridden on that, that would have got you to Mars in a little over a month, about 39 days. But it's a probe. It wasn't made to be a vehicle to carry people or to carry items. NASA's Juno orbiter, which I mentioned in video 1 here, part 1 of this video series, has traveled at over 150,000 miles per hour. But guess what? It's a satellite. You can't ride on it. It's not a vehicle. Now, NASA, when you see the space shuttles that launch and travel, those things can travel at about 17,500 miles per hour. All right? So you can see here, we're just nowhere near being able to travel at light speed and to make these trips to these faraway planets. Even though Mars is one of the closest planets to us, it would still take a full 6 months to get there, a full 6 months to get back. Okay? Well, that's it for the second video in the series. Next, we'll be moving on to part 3 of our solar system. I hope that you learned a little bit today about planets versus stars, what the difference is between a planet and a star. I hope you understood a little bit about the different sizes of our planets with relation to each other and with relation to our sun. I also hope that you were able to wrap your head around some of these vast distances that we see in space and what it might take for us to actually get off of this planet and maybe colonize a place like Mars. In the next video, we'll take a look at the inner and outer solar system. We'll take a look at gravity and the orbits of some of the planets, and we'll talk a little bit about how the solar system formed and the evidence that we have for that. Enjoy. Have a good day.